looking the place where you can learn, master, understand, and enjoy the beautiful advanced physics? If that the questions that you've been asking yourself, I would like to tell you that in advance, today possibly you have met with the right answer. My name is OLENJOLAI Moko Tayai Losingo. Simply just you can call me OLENJOLAI. I thank God by His own grace, I am a citizen of Tanzania, and I would like to dedicate these programs to all advanced secondary students who are taking different science combination and mathematics combinations in the United Republic of Tanzania. I'm very happy to have you today, and just to give you a brief introduction about myself, I thank God by His own grace who has built in me a gift of teaching. So I'll be a teacher who is going to teach you because that is my work, and that's made me to come into this planet Earth and have to do it for the rest of my life. I don't know about you, my students. What is your work? What's your gift? Have you discovered your gift, or you're just studying chemistry and physics? So I would like to challenge you that the meaning of life is in case you discover the built-in gift that everybody has been given by our Creator, God Himself. So I know that how advanced physics is sound in the mind of advanced secondary students, whether they're pre-Form 5 students or pre-Form 6 students or Form 5 students or Form 6 students. Actually, that it's one of the challenging subjects since it's the ordinary physics, the ordinary level physics. It doesn't mean that they know everything about advanced physics. I just know a small part of it, but I'm ready to teach others what I know. I always learn new concepts in advanced physics, and I don't think if I will stop to learn, because also my profession is an engineer. So because I'm an engineer, actual engineering, the simple definitions of engineering is purposeful applications or purposeful use of science. So if you're an electronic engineer, you'll be learning how you can use science to solve real-life problems. So, as I say, that in this moment or in this opportunity that I've got to meet you, whether you're a national or international viewer, I'm going to transform your mindset from fear or from just any kinds of distractions that you used to encounter along your journey of learning and mastering physics. Advanced physics, it's a beautiful subject. It's not the hardest subject, and also it's not the simplest subject. So it depends on your efforts. That's the main thing that I want to tell you. So before even I give you some few introductions about this session, I would like to take this opportunity to welcome our new students who are watching this video for the first time, and even our old national and international students into one of our online schools that's called Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM. Again, I would like to take this opportunity to welcome you into one of our official YouTube channel that's called Tanzania Online A-Level Secondary School in square bracket OLENJOLAIM. What are we doing in Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM? As the name indicate, and the name of the school indicate, we are dealing with advanced secondary students. At this moment, we are dealing with science students and advanced mathematics students, including basic applied mathematics students. So that the group of the students that we're dealing, we are training our level best to teach them, train them, encourage them, mentor them, and guide them and lead them on how they can achieve their goal in science and mathematics. So we'll be focusing on advanced contents. Will be actual that teaching you different sessions and different topics and different concepts about advanced physics. We have so many departments in TOASO because the abbreviations of Tanzania Online Advanced Secondary School in square bracket OLENJOLAI, it is TOASO. So in TOASO we have so many departments, more than 3 departments. One of the departments is called the Departments of Advanced Physics. It's not departments of physics, because when you say physics, actually it is still general. This is a specific department dealing with advanced secondary students who are learning advanced physics, and even college students. In departments of advanced physics, we are just teaching 2 subjects, advanced physics for the Form 5 and advanced physics for the Form 6. Today, we'll be teaching you advanced physics for the Form 6. Wonderful, that's the good news. It doesn't mean that we have retired to teach you advanced physics for the Form 5, but stay tuned. you'll enjoy the stuff. And then in Form 6, according to the new syllabus of advanced physics for advanced secondary education, Form 5 and Form 6 in Tanzania, the advanced physics Form 6C comprises 5 topics. And one of the topics we call the main topic that called the current electricity. I would like to dedicate these contents to all the pre-Form 6 students, all the Form 6 students, all the QT students, all the grade 12 students for the English medium, all the reciters. I would like to encourage you reciters, don't give up. If you have failed physics for the first time, try it for the second time. As just like how a child is trying to walk up. So you should not be disappointed. You should not maybe cancel your visions because you have failed physics. Failure is not the end of the journey. It's just a moment that you have to experience in life, but it does not stop you to achieve your goal. Also teachers, because myself I'm learning from so many teachers in the world, so I would like also to invite some other advanced physics teachers to learn from the contents that I'm going to share. Remember that OLENJOLAI does not know everything about advanced physics. I just know small portions, but I have a responsibility to teach others what I know. How about you? Okay, so then in this main topic of current electricity, we'll be focusing on on current electricity itself. That's the first chapter. And the second chapter is alternating current, or we call it AC theory. Okay, so we are there. So, and this is session 5. We have taught you session 0, session 1, session 2, session 3, and session 4. So this is session 5, which is titled as Factors Affecting Resistance of Metallic Conductor. Again, another thing that I want to say before we start our session, my sessions, all my teaching, means that all my sessions and all my training, I used to give students an opportunity to interact with me through questions. How are you going to ask me questions while you are learning these contents online? That are good questions. The best way that you may use at this moment, you may use the interactive platforms that has been developed by the YouTube community. If you visit our channel, that's called the comments. In comments, you can write a lot of things. Not everything, but a lot of things. Especially in advanced physics, you cannot derive the formula in the comment section there. That's one of the limitations of the comment section. But just write something in the comment section. Give us feedback if you have understood. Ask us questions if you didn't understand. Give us kind of the challenge. Submit the homework there. Tell us what challenge are you facing in physics. Even sometimes if you miss anything else, you can say that thank you for the gift that you are giving, because this is the gift for the Tanzanians. I provide these contents. Usually I used to charge, and it's very expensive to just afford these contents, but right now I said, okay, let me just impact hundreds or millions of students of present and future generation. I believe that you are ready right now to be in business. And even myself, I'm ready. So it's a time for you to take your scientific calculator, because we have some computation. Take your exercise book, take your pen, have a fresh mind, and then be ready, and then don't fall asleep. So you have to make sure that you keep in watch. So let us do a business and let us transform your mindset. So the quick review of session 4. So in session 4, we've been dealing with metallic conductor. So conduction in metallic conductor. How electric current is conducted in metallic conductor. That's the question that we've been trying to answer. And if you do remember that we drew a metallic conductor as a cylinder, it doesn't mean that we have thick metallic conductors. Some of them are thinner, for example, copper wire is thinner, but just we draw it in this big picture in order for you to understand, right? So you have thick conductors and also you have thinner conductors. Okay, so we say that this one, for suppose that here we have a length that we call TR, and then here we have something we call the number of electrons. Okay, we have number of electrons. If you apply a potential difference here, and then these electrons will be moving, will be in motion. So if electric current, so it means if electrons will be flowing in this direction, then electric current will be flowing in opposite directions due to conversion. So this metallic conductor, we can measure its radius. So because we can measure its radius, we can compute also its cross-sectional area. Okay. And then we can determine the magnitude of electric current. So remember that here we said we have something called number of electrons per unit volume, which is N is equal to NV, right? And then we did some derivation, which is very interesting for me. I don't know about you. Finally, we got an expression of electric current. If you want to determine electric current flowing through any conductor, is given as number of electrons per unit volume times what electronic charge times what drift velocity and then times what cross-sectional area. And I told you that in most cases we used to give students tricks that this formula is called never. So never N stands for number of electrons per unit volume, electronic charge, drift velocity, cross-sectional area. Why? Because these electrons will be moving in this direction, so these electrons will be moving with a certain velocity, which is drift velocity, which might be a uniform velocity. Okay? So that's one of the expressions that we have derived and it has been useful. But again, we taught you about momentum. What will be the momentum of electrons? Momentum of electrons in metallic conductor. So that's what we have taught you. But lastly, we taught you how you can derive the formula that related resistance of the metallic conductor with mass of electron times length then of what? Of a number of electrons per unit volume times electronic charge square times cross-sectional area of the conductor times relaxation time. This is the last expressions that we spent almost more than 20 minutes to derive it. If you missed the derivations of this formula or this formula, please just visit our official YouTube channel that's called Tanzania Online A-Level Circuit School in square bracket OLENJOLAIM. Visit the playlist written Current Electricity. You'll find session 4 and you'll enjoy all of these contents. So that's what we have covered in brief in session 4. I believe that you are ready to go with me in session 5. Are you ready? So session 5, let us start with corrections of the homework, which is not well stated in previous session. So correction of what? Of homework. That was homework 4. Okay? Corrections for the homework 4. So the question states that, so this is the question. Given the formula which I've already taught you how you can derive, that relates resistance and its factors resistance and its factors that affect it is resistance is equal to mass of electron times length of the conductor, number of electrons per unit volume times electronic charge square, cross-sectional area times relaxation time. Then the question states use it to derive, then the video ended there, derive what? The formula of what? Of Roman 1, conductive resistivity of metallic conductor, resistivity of metallic conductor is the flow of electric current. Then use it also to derive conductivity of metallic conductor. That's the question. Be serious, please, because physics needs serious students. So solution. So the good thing, the question asks you or tests you your capacity of deriving, not computing. So solution. So the first step we say that, okay, first step, say that recall given what? The given formula. Call the given formula. So the given formula is what? Resistance is equal to mass times length of what? Number of electrons per unit volume, electronic charge, cross-sectional area, relaxation time. Okay? So with this formula, what do we say? So suppose that this is equation 1, because we need to derive what formula for resistivity. Again, we say that recall the relationship, recall the formula, relates what? Formula that relates resistivity, resistance, length, and cross-sectional area. Okay? So we used to teach you in O level that resistance is very proportional to the length and inversely proportional to the cross-sectional area. Right? That's the resistance of the conductor. So if we omit this proportionality constant, we have resistance is equal to conductivity times length over cross-sectional area. So if that's the case, let us make resistivity the subject. So we say that, okay, so this is over 1, so we cross multiplication. So we have what? Or first of all, before we deal even with this, say that the resistance is equal to resistivity times length over cross-sectional area. This is question 2. So simply go into the second step. Second step, we say that equate the relationship between question 1 and question 2. Equate question 1 to question 2. Okay. So we say that resistance is equal to resistivity, resistivity times what? Length of our cross-sectional area. That is equation 2. This is equal to the mass of electrons times length of the conductor. Then we have what? Number of electrons per unit volume, electronic charge, cross-sectional area, and relaxation time. So means that is. So if now replace this one, it means length and length cancel, cross-sectional area and cross-sectional area cancel. So resistivity of a conductor is equal to mass of electrons of what? Number of electrons, electronic charge times relaxation time. So this is the formula required. So whereby this is what? Resistivity and M stands for what? Mass of what? Mass of electron. Then N stands for what? Number of electrons per unit volume. And T stands for what? T stands for relaxation time. So that is this the answer for Roman 1. So for Roman 2, we need the conductivity, right? So conductivity, which in physics we use this notation for the conductivity of what? Of metallic conductor. How can you derive from the same form metallic conductor? Okay, so we go into the third step. Third step. The third step, we say that recall relationship between conductivity recall formula of conductivity in relation to what? To resistivity. So we taught you that in O level, conductivity is equal to reciprocal of resistivity. Okay, reciprocal of resistivity. Okay, so we may use this formula, but remember that the said equation, this one, we derived it from this formula. So you'll be spending much time, you'll be spending a lot of energy, while the formula of conductivity, the formula of resistivity, can help you to navigate. So for that case, we go into the, so suppose that this is equation what? This is equation 4, and suppose this one, it's equation 3. Okay? So you say that, if that the case, we go into the first state, substitute equation 4 into equation 3. So substitute equation 4 into equation 3. So equation 4, we have conductivity is equal to 1 over resistivity. Okay, so this will be equal to 1 over what the resistivity is equal to mass of electron over number of electrons per unit volume times electronic charge times relaxation time. So we say that conductivity is equal to what? Is equal to 1 divided by what? Mass of electron NA square T. So this will make what? 1 times what? NAT square of what? Mass of electron. So conductivity is equal to what? Is equal to number of electrons times electronic charge times relaxation time over mass of electrons. So this is the final expression or formula which you are going to use it in solving problem. Okay? So we have defined, in this part we define, this is stands for resistivity, M stands for mass of electron, N stands for number of electrons per unit volume, T stands for relaxation time. Maybe the new terminology here is the symbol for conductivity, whereby this one represents conductivity, represent conductivity of what? Of metallic conductor. Represent conductivity of metallic conductor. Okay? Then you are done. That was the homework. Wonderful. So let us go into the subtitle above, which state that factors affecting resistance of conductor. These are very important factors. You as physicists or physics student, you have to understand these factors and remember them. So factors affecting conductivity of metallic conductors. So factors affecting conductivity of metallic conductors. So we want to start this. So we say that the factors that affect the conductivity of metallic conductor are deduced from the formula that relates resistance, number of electrons per unit volume, electronic charge, relaxation time, and mass of 40, mass of electron. Did I forget anything else? Yeah, relaxation time. Relaxation time. We have mass, resistance, number of electrons per unit volume, and then what cross-sectional area, AG, cross-sectional area, and mass of 40 of electron. How? Recall session 4. Recall what he taught you in session 4, but also he repeated in session 5. We told you that resistance of metallic conductor is equal to mass of electrons. It's a product of mass of electrons times length of the conductor over number of electrons per unit volume times electronic charge square times cross-sectional area times relaxation time. Okay? So from this one, so remember that. Mass of electron, so we say that whereby M, mass of electron, this is mass of 40 of electron, which is constant, which in scientific calculator we know ME, and this is 9.1 exponential 30, negative 30 kilogram. Right? So it's constant. Again, we have A, which is standing for electronic charge. This is electronic charge, which is 1.9 exponential 1.6 or 1.9? 1.6 exponential negative 19. Yes. Negative 19 what? Coulomb. Right? And then we have what? Length of the conductor, it can vary. Sectional area, it can vary. Relaxation time, it can vary. We have number of electrons per unit volume. The number of electrons per unit volume. Number of electrons per unit volume, okay, depends on the length and cross-sectional area, but when the conductor has already been made, it cannot be changed. Okay, so this is equal to number of electrons, okay, over volume. So for that case, we physicists, including yourself, you're an excellent physics student, we say that when you have resistance times mass over number of electrons per unit volume times electronic charge square, then this one, we can group them together. Then you have length, we have cross-sectional area, and we have relaxation time. So all of these three variables, or three physical quantities, are constant, right? Constant. So you say that, okay, so suppose that this is equation 1, and now because we've dropped these terms, you can call this equation 2. So you say that if that's the case, you say that because we are deducing factors affecting what? Affecting resistance of what? Or conductions of metallic conductor. So you say that let mass of electrons, the ratio mass of electrons of a number of electrons per unit volume, then times electronic charge to be constant. Okay. So if that's the case, we say that, okay, so we have what? Resistance of metallic conductor is equal to constant K times length over cross-sectional area time. But this is proportionality constant. For that case, you can say that resistance is directly proportional to the length and inversely proportional to the cross-sectional area, inversely proportional to the relaxation time. Very important deduction. There's no need for you to claim this stuff. So we say that from here we say that not length of conductor is not fixed. It's not fixed. Again, cross-sectional area is not fixed. then relaxation time is not fixed. So they can vary. For that case, also the resistance of metallic conductor is not fixed, it can vary. For that case, we say that the factors that affecting conduction of metallurgy of metals are the first factor is length of a conductor. The second one is cross-sectional area. Cross-sectional area. Then the third one is relaxation time, which is representing what? Relaxation time, which is representing temperature. This is the parameter that we learn in this session that representing what? Temperature. Remember, electrons in the conductors, they can travel or they can vibrate. However, also, it depends. If assumption is made that the number of electrons is constant, that's fine. But sometimes the size of the conductor can vary. Thus, it can make the number of electrons flowing to volume also to vary. Okay? So this factor, the rest, this one is always constant. This one is always constant, but this one, it depends on the situation. Okay? Okay? So simply from this equation, we can find that, yeah, so even this factor, it can play a great part in affecting the resistance of the metals. So let us start each factor and then we'll go into the computations or into the problem solving. So let us say that the effect of what? The effect of length. So let us start with length of conductor. How does length of conductor affect the resistance? Length of conductor. 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 So what the relationship between length of the conductor and resistance, that's all. So say that from what? From the formula of what? Of resistance is equal to mass times length over number of electrons per unit volume times electronic charge, cross-sectional area, relaxation time. So you say that from there, this one, okay, resistance of conductor relate with what? With length of conductor proportional. means that resistance of a conductor resistance of a conductor is directly proportional to the length of the conductor. So if you increase length of conductor, you increase resistance of conductor. Okay? If you decrease the length of conductor, then you decrease the resistance of the conductor. So the relationship is that resistance is there proportional to the length of 14 of the conductor. So that's the fact, and you have to remember every time when you're dealing with this stuff, because we have a great contribution in the life of working, in the life of learning physics. When you say conductor, you should have a good understanding. Basically, in physics, whenever we talk about conductors, we're talking about wires. Here I have a demonstration of the two conductors, which actually will teach you these factors and understand for the rest of your life. You'll never forget it. This is one of the conductor. Okay, so one of the conductors is short in terms of length, right? So if we consider the fact of length itself, it means this conductor will have small resistance compared to the other one, which is longer than this, right? So for example, this one, then we have another conductor which is longer. So you see, so longer and even part of it will remain. So according to this fact, resistance of this longer wire is higher compared to the resistance of this shorter wire. Okay? That's the meaning. So that's the first factor of 14 of length. And sometimes you can maybe deduce a simple formula that resistance can omit this proportionality and introduce proportionality constant. So you can have something, an expression like this one, which you use it to reduce the resistivity of the material. Okay? Then we have the second factor. I'll be using this one also to demonstrate for the second factor. Second factor that affects the resistance of of the metallic conductor. Cross-sectional area. So cross-sectional area of a conductor can affect the resistance. Cross-sectional area of 14 of conductor. Sectional area of conductor can affect what? Resistance of a conductor. How? So remember the key. From the formula that I taught you how to derive, okay? From the formula that I taught you derive resistance is equal to mass times length of a number of electrons per unit volume times electronic charge square times cross-sectional area times time. So from that, so you say that we find resistance of what? Of conductor relates with what? With cross-sectional area. How does they relate? So relate is cross-sectional area inversely. So we say that when cross-sectional area when cross-sectional area of conductor. So here we say that it means that the resistance of a conductor is directly proportional to the length of the conductor. Okay. So when the cross-sectional area of a conductor increases, then its resistance decreases. So you see the inverse proportionality. So when the cross-sectional area of the conductor increases, then its resistance decreases, and the vice versa. Make sure that you remember this phrase, and vice versa. Okay? So what does it mean? If you keep mass, length, number of electrons, electronic charge square, and accretion time t, then you can find resistance inversely proportional to the cross-sectional area. So from this sentence, say resistance is inversely proportional to the cross-sectional area. So when you increase the cross-sectional area of the conductor, then you decrease what? Resistance of the conductor. And when you decrease the cross-sectional area of the conductor, then you're increasing what? The resistance of the conductor. So if you want to replace the proportionality constant, the proportionality sign with proportionality constant, so we say that this resistance is equal to K times what? Times 1, but over what? Cross-sectional area A. So resistance then proportional to 1 over cross-sectional area, and then that's the case. So resistance is equal to proportional to the cost of cross-sectional area. Okay, so if that's the case, also this is kind of the simple formula that you have to remember. You may use it. And when you say about cross-sectional area, not before, when you say about cross-sectional area of conductor, when you say about cross-sectional area of the conductor A is given as what? It's given as pi d square, so it depends the diameter of the conductor over 4, or pi r square. So cross-sectional area that we are talking may be obtained if you know the diameter of the wire, or if you know the radius of the wire. So this is very important formula for the rest of your life in all the computation problems of physics. Okay? So now, from this fact, what the relationship between resistance and diameter of the conductor? Huh? That's sleeping. Simple. What the relationship between resistance and diameter of the conductor? Inversely. Inverse proportional. Yeah, it's true. And with radius, still inversely proportional. Okay, so those are the two factors. Just to do the demonstration. When you say that, here we still have our two conductors. This is one of the conductor. It's conductor with large cross-sectional area. When you say cross-sectional area, it's area around this wire. Okay? So this is the conductor which have large cross-sectional area. So its resistance will be small, right? Why? Because when you increase cross-sectional area, you increase what? You decrease what? You decrease resistance. But again, we have another thin conductor, right? With small amount, with small cross-sectional area. So expect that if you examine the factor of cross-sectional area, this wire will have high resistance comparing to this one. Right? Yeah, so that's a fact, and you have to bear it in your mind. If you have any question, don't hesitate to ask in the comment section, because we are here to help you to understand and not to claim. The home of, I mean that to also, it's a home of understanding. So if you've been seeking how you can understand this stuff, then you're in the right place. Ladies and gentlemen, let me teach you about the steady factor which can affect conductivity of the metallic conductor. This one is called the temperature. So temperature of conductor can affect the conductivity. Temperature of conductor. Temperature of conductor. So what does it mean? Sometimes these conductors, the temperature of these conductors might be varying, and that can make your resistance also to vary. So temperature of the conductor. So you say that the resistance of metallic or of conductors depends on what? On temperature. Depends on temperature of what? Temperature of conductors. Depends on temperatures of conductors. So resistance of conductors depends on temperature of conductors. The temperature of conductors, before I speak mathematically, the temperature of conductor affect relaxation time. So affect relaxation time of what? Of current carriers, which are electrons. So resistance of conductor depends on the temperature of conductors, and the temperature of conductor affects the relaxation time of what? Of electrons. So when you affect the relaxation time of electrons, then you affect your resistance of the conductor, right? So when relaxation time is affected, then its resistance, when relaxation time of conductor is affected, then its resistance will change. So it means that resistance depends on the temperature according to the relaxation time. When you say relaxation time, it means vibration times of electrons. Because you say if you apply potential difference at one end of the conductor, then electrons start to move or start to vibrate in order to conduct electricity from one point to another point. So when that time of relaxation of collision between, for example, that here we have an electrons at this point, so suppose that this is the conductor. So this is the conductor. I want to explain the relaxation time. This is the conductor, and we have, let's suppose that the distance between these two electrons is there. Is that one, right? And then so you apply a potential difference here. So you apply a potential difference which will contains electric field to drive that potential or drive electric current there. Then what happens? So it means the first electrons that you receive these kinds of energy, electric energy, will be this one, right? So this one can vibrate to this point or it can travel. So it means that, for example, for these electrons which are separated apart like that, you can find that this is separation time 1. Okay? So that separation time is quite different if you have another electron here. So separation time between this and this will be, let's say, T2. So it means that T2, but also depends on the amounts of the potential difference supply. But simply relaxation times, it's a time when these electrons vibrate or move and hit another electron. Go together. So before we explain that how temperature affects time, let us speak mathematically first, then we speak what? Mathematically first, and then we speak generally about what it means speaking. So say mathematically, you have to recall from resistance is equal to mass of electrons times length over number of electrons per unit volume times electronic charge times cross-sectional area and time. So suppose that this is equation 1. So we say that assume number of electrons per unit volume cross-sectional area and cross-sectional area so assume length or number of electrons per unit volume and cross-sectional area are constant. Constant. So from that fact we say that resistance now is equal to mass times length over number of electrons times electronic charge times cross-sectional area times 1 over cross-sectional time. So because these are the constants, we can say that we can let that K is equal to mass times length over number of electrons per unit volume times electronic charge times cross-sectional area. So resistance is equal to proportional constant K over relaxation time. So for this fact, you may find the resistance of metallic conductor is inversely proportional to relaxation time. So when relaxation time between electrons increases, resistance of the conductor decreases, and vice versa. Let me repeat. When relaxation time between electrons of the conductor increase, means resistance decrease. And what can increase the relaxation time of electrons? Okay, so resistance is inversely proportional to relaxation time. My question, if relaxation time between electrons increases, relaxation time when electrons increases, then resistance decreases, right? When relaxation time decreases, then resistance increases. Okay? At the point that you have to note. Okay. So from there we can write a fact now. And the fact is, we say When metallic conductor is heated, the atoms in the metal vibrate with greater amplitudes about their mean position. Due to increase in the thermal energy of the conductor, the velocity of free electrons also increases. Loss of free electrons sorting. Pardon? Increases. Consequently, the number of collisions between the free electrons and atoms increased. So if the number of atoms increased, what do you expect? Huh? You tell me you've already understood. How is this concept you say that is said? So you say when you increase the collision time, we decrease what? Resistance, and vice versa. That's the point. Okay. I'm still explaining the effect of what? Of temperature in metallic conductor. When a metallic conductor is heated, when a metallic conductor is heated, so you say that then the atoms vibrate, and the atoms in the metal when the atom so when a metallic conductor is heated, the atoms in the metal starts to vibrate. Okay, so say that the atoms in the metal start to vibrate with greater amplitude. Okay, so we say that when a metallic conductor is heated, for example, these wires, then the atoms, the metallic conductor contains atoms, for example, copper metallic conductor, or we can have constantance metallic conductor, we can have iron metallic conductor. So when they are heated, the atoms in the metal starts to vibrate with a greater amplitudes about their mean position. Greater amplitudes about their main position. About their main position. So say when the metallic conductor is heated by heater, any source of heat, the atoms in the metal start to vibrate. It's a greater amplitude about their mean position. Okay? So we say that we have a metallic conductor, we heat the atoms in the metal, start to vibrate. When we say vibrate, it means executing which type of the motion? Simple harmonic motion, right? So it means up, down, up, down, up, down, up, down. We say greater amplitude about their mean position. Due to increase in thermal energy, so due to increase in what? In thermal. Thermal means heat. Thermal energy. Inside of what? So due to increase in thermal or heat energy, then we say that what happens if the thermal energy increases in the metal? What do you think about thermal energy, the increase of thermal energy? So it's simplified, right? So say if the thermal energy is added, we're expecting say that due to the increase in thermal energy, the drifting velocity of electrons will also increase. Okay, so we say that the first sentence, when a metallic conductor is heated, so we are examining the factor or the effect of temperature to the resistance of the conductor. The atoms in the metal start to vibrate with greater amplitude about their mean position. What does that mean? Before even I continue, mean that we say if electrons start to vibrate, suppose that this is the y-axis and this is horizontal axis. So we say that with greater amplitude means that electrons start to execute simple harmonic motion. So this is the amplitude. So we say amplitude is the distance from the mean position to the maximum displacement. Okay? So if that is 30, that's what happens. So there's a vibration. So vibration is to and fro motion. So electrons start to experience to and fro motion. So again, the second sentence, due to the increase in thermal energy, inside the metallic conductor, the drifting velocity of electrons will increase. Why? Because the thermal energy break the bonds or break any kinds of the limitation, because remember that even the valence electrons is weakly attracted by the nuclear attractive force, right? So the nucleus of an atom is still attracting those. But if the temperature, or for example you apply the thermal energy, that thermal energy is going to break that bonds or that attraction force, so electrons will be more free. Are we together? So the increase of drifting velocity will also affect what? The relaxation what? Time. Okay? So increase the relaxation time. So the increase of drifting velocity, and why do we call it drifting velocity? What the reason? Because it is average velocity. Right? It's average velocity. You have so many electrons, and then the electrons they attract that vibrating into the three-dimensional. So we have x-axis, y-axis, and z-axis. So that's why we call it drifting velocity, because the average velocity. The increase of drifting velocity due to temperature reduces what? Reduces the relaxation, reduces the relaxation time. Why? And vice versa. Okay, why? Why? Because velocity, for example, is equal to distance over time. So for this case, velocity is inversely proportional to time. Okay? Okay? Velocity is inversely proportional to time. So if the relaxation time is reduced, what will happen? So you say that from resistance is inversely proportional to relaxation time from this one. Say that if relaxation time is reduced, then the resistance of what? Of conductor will be increased. So if relaxation time is what? Reduced. If relaxation time is reduced, then the resistance of the conductor will be increased. Due to this fact, we say now, therefore, the resistance of a conductor is directly proportional to the temperature. Very proportional to the temperature of the conductor. And what? And vice versa. So this is the fact. So for that fact now we say that resistance of a conductor is very proportional to temperature. So it means that we can say that resistance is very proportional to absolute temperature. You can also remember the kinetic theory of the case, but this is enough about the effect of temperature, or the effect of temperature, the resistance of the conductor. If you have any question about factors affecting the conductivity of metallic conductors, then don't hesitate to ask in the comment section. Then let me present to you a little bit, let me present to you two terminologies. Then we go into the business. We have the term called the potential difference. Potential difference. Potential difference. Potential difference. Potential difference. So potential difference, we say that, what is potential difference? What is potential difference? So we say that potential difference in current electricity we define as is the work done by external agent. Work done by external agent in taking, so the work done by external agent in taking a unity charge from a point to another point. In taking a unit charge from one point to another point in the conductor. So potential difference is the work done by external agent, taking a unity charge from one point to another point in the conductor. So for that case, we say that we have say that from, you have to recall what we taught in electrostatic. Electrical potential is equal to work done over point charge Q. So electric potential is equal to work done over the point charge Q. So if that's the case, we say that work done is equal to electric potential times point charge Q. But according to the dimension, we remember that work done is equal to energy. Work done is equal to energy. They are measured in joules. So work done is equal to energy. For that case, here we are learning about current electricity, so we are dealing with electric energy. So it means that work done in taking what? In taking a pointy charge, work done in taking a pointy charge is electrical energy. It's electrical energy. So simply electrical energy is equal to electric potential times point charge. But from what we told you that quantity of charge is equal to electric current times time. Do you remember this expression? So if that's the case, we take equation 2 and substitute in equation 1. So we get what? Electrical energy is equal to what? is equal to electric potential multiplied by current. So simply say that electric energy, it's a kind of simple formula that we used to say it is ITV. Again, another technology that we want to cover, which we made it in solving problem, is called electrical power. Electrical power. So what is electrical power? So simply say that electrical power is the rate of electrical energy. So power, electrical power, is equal to electrical energy of what? Over time. So electrical power is equal to energy, which is ITV over time. So time and time cancel. This is equal to current times voltage. So simply say that electrical power is equal to product between electric current and potential difference. It's a formula which is familiar for many advanced secondary students, so nothing new there. The SI unit, just to remind you of electrical energy. The unit of electrical energy is joules, and the unit of electrical power, or unit of power in general, is what? Watts. Okay? So if that's the case now, let us start at least to solve a few questions before I end this session. Don't remember exactly the number of questions or the number of examples. So, yeah, so you can check. I'm not sure if it's example 1. I'll just check. How many electrons flows? How many electrons flow through the filament? Through the filament of what? Of 120 volts. And the 60 watt electric lamp. In 1 second. how many electrons flows through the filaments of 120 volt and 60 watt electrical lamp in 1 second. That's the question. It's not a difficult question. It's the simplest example. So for you, it's writing the numbering, this example. Are you sure? So data given. We have electric potential. The potential difference, which is V, is equal to 120 volts. So in a being given power, which is equal to 60 watt at the power of 40 of the electric lamp. In a being given time, this is equal to 1 second. What are we asking? Number of what? Number of electrons. Number of electrons. This is what we require. So the second step, we have to recall two formulas that we taught you in session 4 and session 5. Recall the two formula according to the data that we're being given. The first formula, the formula that can help us to find power. So the formula that can help us to find power is electric current flowing through the electric lamp and potential difference. This one. Okay? So this will be the first equation. Second step, the same step, recall again, in the second step, recall the formula that can help us to compute the electric current depends on the number of electrons per unit volume. Okay? So you say that I is equal to number of electrons per unit volume times electronic charge times derivative velocity times cross-sectional area. So what are we looking for? We are looking for N. Okay? Looking for N. No, these expressions will not give us because we don't know the cross-sectional area. So we have an expression, we don't know the cross-sectional area, we don't know the derivative velocity. Okay? So the best expression that can help you here, you have to remember what we taught you in electrostatic. And basically we taught you that quantity of charge is equal to electric current times time. But also quantity of charge is equal to number of electrons times electronic charge. So electric current times time is equal to number of electrons times electronic charge. So this is what is equation for equation 2. But we can simplify this equation 2 before substituting equation 1. So you can divide by time, and on this side divide by time. So electric current is equal to number of electrons times electronic charge over time. This is equation 2. Why did I recall expressions that give us quantity of charge, which is equal to number of electrons times electronic charge, which is equal to what? Electric current times time. Because according to the data that I've given, the question did not state anything about derivative velocity. The question did not state anything about radius of the conductor or diameter of the conductor or cross-sectional area of the conductor. So it means that I will have a single equation that can help me to determine maybe number of electrons per unit volume. But again, the questions ask you the number of electrons, not the number of electrons per unit volume. you have to understand the difference between capital N and the small n. Okay? So, after that, we go into the third step. The third step, we say that let us substitute equation 2 in equation 1. So substitute equation 2 in equation 1, we say that power, which is given, is equal to number of electrons times electronically charged times electric potential over time. Okay? So number of electrons times electronically charged over time. So we know the power, we're looking for this one. So we can cross multiplication, make n the subject. So we have power in numerator divided by what? Electronically charged electric potential is equal to number of electrons. Okay? So number of electrons is equal to power. Power is 60 watt times time, it's 1 second. Electronically charged is 1.9, 1.6, yeah? 1.6 to negative 19. What's the electric potential? 120. So the number of electrons you have to use, you have to take your scientific calculator. If you don't have, please go into the descriptions of this video to see how you can order the scientific calculator from our TOASO library. So when you do that computations, the number of electrons will be 3.125. 3.125 exponent 18. So therefore, the number of electrons flows through the filament. Number of electrons flow through filament is 3.125 exponent 18. Okay? So this is example, ladies and gentlemen. 32, 4, 5. I'm not writing the number of questions. I think I left how many homework? 1, 2, 3. So that's 4. So this is example 5. For the homework are the questions. So I'm still doing simple question just to build the foundations in your mindset. What is drift velocity? What is drift velocity of electrons? Of electrons in a copper. In a copper conductor. Copper conductor having a cross-sectional area having a cross-sectional area of 5 from negative 60 meters square. If the current is 10 ampere, assume there are 8 exponent 28 electrons per meter cube. That is one of the simplest questions in current electricity. So let us read the question together. What is drift velocity of electrons in a copper conductor having cross-sectional area of 5x to negative 6 meters square? If the current is 10 ampere, assume there are 8 exponent 28 electrons per meter cube. You can pause the video and then try this question yourself. Once you try in the rough paper, you can come and check your response solution. So the first step, you say that data given. So the data given, you say that we have drift velocity, this is what is required. Then you have what? You have cross-sectional area. This is what? 5 is for negative 60 meters square. Then you have what? You have number of electrons. Number of electrons per unit volume. Unit volume, this is N, is equal to 8 exponent 28. Electrons per unit volume per meter cube. Then we are given what? The magnitude of electric current. So current, which is direct current for this case, because it is what? A copper conductor. Can be direct current or alternating current, 10 amperes. So the second step, you have to examine the given data and think outside the box in how you can get the required physical quantity. So second step, we say that recall the formula that relates that base current is equal to number of electrons per unit volume times electronic charge times drift velocity times cross-sectional area. We are looking drift velocity, so we divide by NEA, then here we divide by NEA. So simply say that drift velocity, this is just a symbol for the drift velocity. You can use the V without subscript of D, NE, so this is NE times cross-sectional area. So the electric current flowing through this conductor is 10 ampere, and then divided by number of electrons, so it is 8 exponent 28. Then times electronic charge 126 exponent negative 19 times what? Cross-sectional area, which is 5 exponent negative 6. Negative 6. So when you use a scientific calculator, you can find that this is meter square This is Coulomb. This is electron per unit meter cube. So the drift velocity will be in meter per second. So the drift velocity is 1.56 exponent negative 4. 1.56 exponent negative 4 meter per second. So therefore, drift velocity of what? Drift velocity of electrons. The average velocity of electrons in a copper conductor is 1.56 exponent negative 4 meter per second. The response. Remember that my classes are incomplete without questions from the students, and also my classes are incomplete without leaving the homework to students, because the homework makes students think differently. So right now, it's a time for the homework. Tell your neighbor, it's a time for the homework. After giving you that homework, I will end session 5, and I would like to invite you in session 6, which I expect you to focus on problem solving. Having formulas, these are still simple problems. I have more than I've prepared for these sections. I have prepared 16 questions for this. However, that time will not allow me to do all the questions, but I believe God will help me to choose those challenging questions to mostly of physical and online students, faster learner, intermediate learner, and even slow learner. So this is example 6. Example 6. This is homework 5. So be careful. Calculate drift velocity. Calculate drift velocity in a copper wire. In a copper wire of diameter 1.6 exponent negative 3 meter, carrying a current of 10 ampere. 10 ampere given density of copper. Density of copper is 9.9 kilogram per meter cube. Atomic weight of copper is 65.5 gram mole. Assume each atom of copper contribute 1 free electron. One free electron for conduction. That's the question that you have to try as a senior student to answer. Let me read in case that you miss or you can't read some of the words. The question states that calculate drift velocity in a copper wire of diameter 1.6 to the negative 3 meter, carrying a current of 10 ampere. Given that, or given the density of copper is 9 exponent 9 kilogram per meter cubic. The atomic weight of copper is 65.5 gram per mole. Assume each atom of the copper contain or contribute 1 free electrons for the conduction. Assume each atom of copper contributes 1 free electrons for conduction. Ladies and gentlemen, this is the end of session 5, which has been titled as Factors Affecting the Resistance of the Conductor. I would like to take this opportunity to thank you for paying attention and for joining me from the beginnings to the end of this session. I believe that this session has transformed you from the old state to the next state. I would like to take this opportunity also to invite you in the next session. First of all, before inviting you in the next session, you can access our previous session, session 0 of current electricity, session 1 of current electricity, session 2 of current electricity, session 3 of current electricity, session 4 of current electricity. You can access them in our official YouTube channel which is called the Tanzania Online A-Level Circuit School in square bracket OLENJOLAIM. But again, you can access them in one of the playlists that called the current electricity, where you can go through all of this, all the videos. Means every session is in a single video. You have to make sure that you begin the session and you end it before going through the next session. Another thing that I would like to let you know, or just remind you, please use the comment sections of this video to ask me questions, to submit your homework, to give me the feedback if you've understood, and even also to share with me the testimony, how these sessions of current electricity transformed your life from the fear of physics or advanced physics into the victory moment of advanced physics. I know that it might be a hard work, it will be a work of so many days, but even ourselves, we have been pursuing this subject consistently. Okay, so at the beginnings, we have given up, we have saw that we cannot manage to maintain what we have to maintain, or to keep it up. So, but later on, as long we've put a lot of effort, later on, we encountered ourselves that, yeah, God is at work. So another announcement, I would like to invite you, in case you want to offer your freely Thanksgiving for this program. This program is actually very expensive to get these contents. It's very expensive, but thank God who have paid the cost for you. So you can send your freely Thanksgiving through that telephone number 0759 745331, and registered name is OLENJOLAI. You can. When I say about your freely Thanksgiving, don't send because I said. Send because you want to offer your freely Thanksgiving from your heart, and from just because you have to make sure that you offer it in generosity, right? So it means that you offer it to please God and not to please me. Okay. So again, you can send freely your Thanksgiving of an amount of 50 Tanzanian shillings, 100 Tanzanian shillings, 500. Okay, 10,000, maybe 1 million, 100,000. So myself, I used to offer my free willing Thanksgiving in this project day after day. How about you? And God is blessing me from time to time and day to day because of just offering Him through this program, which will impact millions of students of present and future generation. Okay, so another thing that I would like to insist you can share these contents with other students to let them know. I know that sometimes you have some of your classmates, some of your schoolmates, they have been suffering with advanced physics. Maybe they have been studying in a wadi advanced secondary schools. Right now with these programs, you can access these contents anywhere at any time. So may God bless you and keep you. I will keep on praying for you. And also I ask you to pray for me in order to make sure that you will do our assignment on the planet Earth. So be blessed, keep enjoying advanced physics, don't give up, keep struggling and keep working hard until you achieve your success, because everyone wants to succeed. So be blessed until we meet in session 6. See you.